All right, welcome everybody. Time for another Dan webinar on decompression sickness with the Professor Simon Mitchell. From my side, welcome Dive Nation. It's great to have you join yet another supercharged Dan webinar. My name is Morne Christo, your host and also the CEO of Dan Southern Africa. And from my side, really a big thank you for making time to join this webinar. And I'd also just like to thank you all for supporting Divers Alert Network, which helps build safer dive communities around the world. Now, our talk topic this evening is decompression sickness and inflammatory disease. It's going to be a great presentation. I hope you're ready for it. And yeah, I received loads of comments via the social media blast I put out there. So for those folks that had questions, well, I'm sure it's going to be answered soon. Just a couple of webinar basics. Your video and mic's turned off. That's just to avoid any interruptions during the presentation. And if you have any comments either now or during the presentation, please use the comments box, depending on which device you are. It'll either be to the left, right, or bottom of the live stream. And for now, while you wait for me to finish up with all the introductions, why not introduce yourself and tell us where you are in the world and what your expectations are of the webinar. And during the presentation, if you have any questions, also please make use of the comments box. All I ask is that you use hashtag ask and then followed by your question so that it'll be easy enough to pick up any questions amongst the comments, which we'll address right at the end of the presentation. So don't feel like we're neglecting you. We just prefer to do it that way. Okay, so as usual, the webinar replay will be available tomorrow via the Dan Southern Africa YouTube channel. And you'll also receive an email with the link to the replay along with a bunch of resources, in particular, some that will refer you to Professor Mitchell's channels, obviously some Dan resources that you can access, and then the webinar sponsor, which is Scuba Pro Southern Africa. You can see all the products and services they offer, along with how you can find any of their dealers for those folks within the Southern Africa region. So a big shout out to them. Thank you very much. From our side again, thank you for supporting Divers Alert Network. If you haven't joined yet, why not join today? If you find yourself in the Southern Africa region, you can learn all about what we offer and how to join via our website, and that is simply dansa.org. If you're in the United States region, you can just go to the dan.org site. In the European region, it's daneurope.org. And if you find yourself in the Asia Pacific region, it's danap.org. And to all the active Dan members, thank you for your ongoing support. Without you, initiatives like these won't be possible. Now, if you feel like helping us grow our YouTube channel, I've activated the YouTube Super Chat feature. And essentially what that does is you can click a little icon that looks like a dollar sign to the left, right, bottom, or top of the comments box, again, depending on which device you're on. And that'll bump up any comments or questions you might have. It'll highlight that. Or if you just want to show your support, you can choose a bunch of stickers. So if you do decide to do that, thank you in advance for your support. Now, as usual, I have a free Dan gift for the folks joining us today. It's a Dan Guide on Decompression Sickness and forms part of the Health and Diving reference series. Now, it's fairly easy to get hold of it. All you need to do is just scan that QR code. That'll pre-populate a WhatsApp message. And all you need to do is just add your name so that I know who I'm talking to, and I'll send you the link to download that guide along with some other free resources from Dan. So yeah, it's fairly easy. Simply scan that QR code. It'll open up a pre-populated message, add your name, and then I'll send you the link to download the guide. Now, I'll make this available right at the end of the presentation for those folks either struggling to scan the code or who might join a little bit later. So there we go. I can see quite a bunch of messages coming through already. I'll answer those while Professor Mitchell is busy with his presentation. Now, while we're on the YouTube live stream, if you haven't subscribed to our channel yet, please do so. That'll help us gain some more traction on YouTube and help share our content with like-minded divers out there. And if you know of folks that aren't on the broadcast, any of your dive buddies, please share this with them now. and ask them to join this live broadcast. They'll really enjoy it, or share the replay link with them. And at the end of the talk, if you enjoyed the presentation, please give us a thumbs up or a like. Again, that'll help the YouTube algorithm promote this amongst like-minded divers like ourselves. All right, so our guest speaker this evening is Professor Mitchell. A brief introduction. He is an anesthesiologist and a diving physician who has widely published over 160 scientific papers. He's co-authored the 5th edition of Diving and Subaquatic Medicine and the Hyperbaric and Diving Medicine chapter for the last 3 editions of the Harrison's Principles of Internal Medicine. And he has a long career in sports, scientific, commercial, military, and exploratory diving. There's much more for those folks that followed all the steps to eventually get onto this webinar. I've got a much more detailed breakdown, but that gives you a good idea. The talk topic, just a quick overview, is decompression, sickness, and inflammatory disease. And in this presentation, Professor Mitchell will discuss the role of bubbles and inflammatory processes in DCS physiology during the talk. So with that said, I'm going to hand over to Professor Mitchell. Let's get started. Just from my side, I'd like to thank him for making the time and also getting up extremely early on his end. And for any of the folks around the world that are either staying up late or had to wake up early, thanks for your support. Obviously, all the South Africans and Southern Africa divers that are joining, thank you so much. So, Professor Mitchell, let me just hand over the controls to you. Let me just see. All right, there we go. Okay, so you are online. Thank you for your time there, and your slides are in presenter view.
Cool, thanks, Mornay. Well, look, good morning, good afternoon, good evening, wherever you are. It's 5 o'clock in the morning, just after 5 in the morning here, so pretty early. I apologize if I yawn from time to time, but that's not through boredom, I assure you. Look, thanks for the opportunity to do this presentation. This is actually a presentation I've given through a couple of platforms over recent years, but I continually update it, and it's a fascinating topic. Look, I just want to start somewhat self-indulgently telling you a bit about me. So I'm like many of you, I suspect, I'm a passionate diver. I'm a technical diver using rebreathers to visit deep wrecks. This is a photo underneath the battleship Nagato at Bikini Atoll. But as Mornay pointed out, my day job is as an anaesthetist here in Auckland, New Zealand. Parenthetically, we tried to steal one of your best and brightest from South Africa a few years ago to come into our field. So some of you will recognize CJ. I don't know if she's on this call, but this was a great, a really fun time when she came and spent I think about a month with us. I don't know why we're smiling so much in that photo. I think we were about to anesthetize a guy that weighed about 200 kilograms. Anyway, we never actually managed to steal her, but we had a good go at it. And look, one of my passions is combining this love of medicine and physiology with diving. And what I particularly enjoy doing is using diving to conduct some of these practically applicable studies. So this is a photo from last year when we took blood gases from an elite free diver at 60 meters and then at the surface before he breathed. A really cool, fun thing to do. And it's a good example of the sort of thing I really love doing. Anyway, moving on to the topic of today's presentation, is decompression sickness an inflammatory disease? And look, it's actually an easy question to answer. Of course it is. It's virtually impossible to damage tissue without inciting inflammation. So inflammation's there in the pathophysiology of decompression sickness. It's just, the real question is what's its true role? Is it the primary mechanism of injury, or is it something else? And that's what I'm really going to address today. So if we've got a dive and decompression on the left-hand side and clinical decompression sickness on the right-hand side, how do we get from one to the other? What is the primary vector of injury? Now, of course, over the years, we've come to view bubbles as the primary vector of injury in decompression sickness, and I'll give you my perspective on that in just one moment. But we have pretty good evidence that there are other things involved. So inflammation is in this paradigm somewhere. And all of the things all of these sort of exemplar paradigms I'm about to mention, we're going to talk about in some more detail as we go through the presentation. But for example, there is evidence that bubbles can incite inflammation, and that inflammation can then contribute to the clinical picture that we see in decompression sickness. There's also evidence that inflammation can arise during diving independently of bubble formation, and that therefore inflammation can be an independent harmful influence in decompression sickness. There's even some evidence that inflammatory processes might promote bubbling. And so these two sort of pathophysiological pathways are intimately interlinked. And then there's even a school of thought that holds that the whole thing's about inflammation. So inflammation occurs independent of bubbling, and its inflammatory process is kicked off by something during our dives, but not bubbles necessarily, that cause clinical decompression sickness. I would put that notion at sort of at one extreme fringe of beliefs around pathophysiology of decompression sickness, and I'm going to talk about that in just a moment. And in fact, let me state up front my own personal view, having been involved in this field for a long time, watching the literature over many, many years, that I believe that bubbles are the primary vector of injury in decompression sickness. And I'm going to present to you what I call my 5-point case for bubbles as the primary vector of injury in decompression sickness. Now, for those of you who are in camp inflammation or deeply interested in that aspect, don't despair. I'm going to come back to that and talk about exactly how I believe the evidence suggests inflammation is involved, and I'm sure it is, and in fact, importantly. But first, my 5-point case for bubbles as the primary vector of injury in decompression sickness. So, point number 1, clinico-pathological correlations. In other words, we see clinical manifestations of disease, and then we link pathophysiological findings of that disease to those clinical observations. And that's been going on in decompression sickness for hundreds of years. It started a long time ago with Boyle, where he observed bubble formation in living tissue and associated those bubbles with the adverse events he was seeing in the animals involved. One of them was famously a snake, where he saw bubbles in its eye. And this was carried on by Paul Beer. With his animal experiments, again, he associated bubbles with decompression sickness manifestations. He showed that it was nitrogen in the bubbles and that oxygen helped with the symptoms. He also showed that slower decompression reduced risk. So we're starting to see the sort of pattern of knowledge that we now accept in this modern day and age. And there have been more modern clinico-pathological correlations. So this is an example from some of James Francis's work, where he was able to demonstrate that the bubble-induced changes that he saw in spinal cord white matter nicely explained the neurological manifestations he was seeing in subject dogs in his experiments. So that's point number 1, clinico-pathological correlations. Point number 2, in this 5-point case for bubbles being the primary vector of injury in decompression sickness, is the inverse correlation of decompression time and risk. It has been demonstrated time after time after time over decades of decompression research, where expert groups have been studying how to decompress from different types of diving, that the longer you decompress for, the less the risk of decompression sickness. Now, it doesn't look exactly like this line, but the line illustrates the key point, that the more time you decompress, the lower your risk of decompression sickness. And it's hard to think of anything else that you might be influencing by decompressing for longer, other than reducing supersaturation in tissues, reducing the number of bubbles that form, and therefore reducing the risk of decompression sickness. So that's point number 2, the inverse correlation of decompression time and risk. Point number 3 in the 5-point case for bubbles as the primary vector of injury is the correlation of venous gas emboli, so venous bubbles, and decompression sickness risk. Now, we see this in animals, we see this in humans. So here's an example from an animal study, relatively recent. Kate Lambrecht's and her group decompressed rats from a provocative dive. Some got decompression sickness, some didn't. The ones that got decompression sickness had higher bubble grades. That's animals. And there's numerous examples of studies like that. In humans, it's interesting. So this is data from the Canadian Navy, Ron Nishi's group. In fact, I think this was David Sawatsky's master's data, where you have bubble grades on the x-axis and the percentage of subjects developing decompression sickness on the y-axis. And as you can see, as the bubble grade increases, you get more decompression sickness. So a clear correlation of venous gas emboli and risk. Now, this is interesting because, and some of you will be noticing this, that even when you have grade 4 venous bubbles, which is a lot of venous bubbles, if you were looking at an echocardiograph of the heart with grade 4 bubbling, it would be close to seeing a whited out right heart. Less than 10% of subjects are suffering decompression sickness. And that observation has been used by some to argue, in fact, that bubbles don't appear to have a particularly good positive predictive value for decompression sickness. And maybe that's evidence that they aren't the primary vector of injury. But I think that's a fairly naive interpretation, because that phenomenon, the high venous bubble grades still not causing decompression sickness in a very high proportion of subjects, is easily explainable by a couple of things. And so why do these bubbles have a poor positive predictive value? Well, one of them is that venous gas emboli don't necessarily reflect bubbling in the tissues where bubble formation might be harmful. So most venous gas emboli probably come from tissues like subcutaneous fat, adipose tissue, perhaps skin, not places where you would necessarily expect to see overt harm if bubbles were forming. So that's point number one. But even more importantly, we now know that to cause harm, venous gas emboli almost certainly need to arterialize across a right to left shunt, like a patent foramen ovale, and they almost certainly, when they do that, need to reach a sensitive tissue while it remains supersaturated with gas, so that these tiny arterialized venous gas emboli will grow when they reach a supersaturated tissue. And I'm going to plagiarize John Reason's Swiss cheese model. It's not a particularly good depiction of it, because the holes aren't all supposed to be in the same place like that. But it's got 4 slices, and that's what I needed, so that's what I'll use. There's a bunch of pathophysiological factors that must line up for venous gas emboli to cause problems. So one of them is you need to form them, and probably a lot of them. Then you need to have a right to left shunt, and it probably needs to be a large one, because a small PFO doesn't readily shunt these small venous bubbles. Then blood and bubbles must cross that right to left shunt, and that can require some kind of provocation at the wrong time, like lifting or straining or some sort of valsalvaring. And then finally, all of that needs to happen at a time when those bubbles can reach into the arterial circulation and reach a target tissue when it remains supersaturated. And if you think about it, having grade 4 venous bubbles only gets you to here. There are still all these other things that need to line up in order for those bubbles to be harmful. And so it's hardly surprising that grade 4 venous bubbles on their own aren't necessarily that predictive of decompression sickness. And I'm kind of laboring that point, but it's actually a very important point, because you sometimes hear the argument, well, you know, if bubbles were so important, why don't we see decompression sickness in grade 4 venous bubbling more often? And I think your answer is right there. That's point number 3. Point number 4 in the 5-point case for bubbles as the primary vector of injury is this association with PFO. So that discussion segues quite nicely into this point. So many of you will be aware that there is an unequivocal and well proven by multiple studies association between PFO, patent foramen ovale, and spinal cord, inner ear, cutaneous, and cerebral decompression sickness, those 4 forms. So the question you need to ask yourself is, what does that association between decompression sickness and PFO tell us about decompression sickness pathophysiology? And the answer, having thought about it a lot, and I'm certainly not the only one who's thought about it, is that something that would normally be filtered by the lungs but can cross a PFO seems important in the causation of those relevant forms of decompression sickness. And I mean, the only thing I can think of is bubbles. Bubbles are removed by the lungs, but they can readily cross a PFO. And we'll come back to that point a little bit later when we're talking about certain inflammatory processes. And finally, in the 5-point case for bubbles being the primary vector of injury is the response to ultra-early recompression. So a few years ago, David Dulett and I went looking for evidence that ultra-early recompression is effective in the context of whether or not we should be considering in-water recompression as a legitimate treatment option for properly prepared and trained groups. And David has access to all these US Navy databases of dives that they did during decompression experiments, where they have a recompression chamber on site and anyone who develops symptoms can actually be recompressed straight away. And it is really interesting, some of these data, they're in this paper, so you can have a look for yourselves. I'm not going to present the data, but what we found was that, very early, ultra-early recompression is extremely effective. And in fact, many of these people get better, not just during the recompression treatment, but as the chamber is being recompressed, their symptoms resolve. So very early response to very early recompression. And it's hard to imagine that if that were an established inflammatory process, that just increasing ambient pressure would turn it off so quickly. It's more likely that this very early response to recompression is due to compression of bubbles and relief of mechanical compression that they're causing in biological systems. So that is a quick walk through my 5-point case for bubbles being the primary vector of injury in clinical decompression sickness. Okay, so this photo here was taken in the Sea of Cortez a few years ago, just pre-COVID, and it shows a few people who some of you might be familiar with. So on the right-hand side of the picture above my left shoulder, the guy that looks like a ghost, that's Lynn Weaver from Salt Lake City, and then to my immediate right is Folke Lind from Sweden, and over on the left side of the picture there is Mark Robbins, who's current president of the UHMS. And I enjoy pointing out when I give presentations at the UHMS that the president needs to learn to clear his mask properly. I mean, that's just an attempt at humor, which is actually useless on these webinar type things. Mark's a great guy and does know how to clear his mask. Anyway, the point is here that I want to make here is that the primary bubbles being the primary vector of injury does not mean the only vector of injury. And so, as I pointed out earlier, there is evidence that bubbles can incite inflammation, and that those inflammatory processes that are incited by bubbles can contribute to the clinical picture in decompression sickness. It's hard to pinpoint when the evidence for this started to emerge, but certainly in the 70s, there were a series of studies published by this guy, Philp, who showed overwhelming evidence of platelet and coagulation activation by decompression. And it was assumed, and in fact subsequently demonstrated, that this was due to bubbles, either directly or due to tissue damage caused by those bubbles. So, for example, Philp incubated platelets with bubbles and found that platelets coming into contact with bubbles, which you can see up near the top of the photo here, those platelets formed their little pseudopods and got activated in the way that we know platelets do. So that direct evidence of activation by bubbles. And then images like this one started to emerge. So electron micrograph of a bubble forming outside a blood vessel, but rupturing into the blood vessel and damaging the basement membrane. We know that's something that turns platelets on immediately. One of the things that Philp did, which I think was important in the context of this discussion, was that in saturation diving, he showed that these platelet changes occurred primarily after surfacing, not during a saturation dive. So the activations that were seen occurred after surfacing, which was more consistent with bubble formation than other processes that were going on during the dive when bubbles wouldn't have formed, of course. Okay, so that's evidence of platelet activation by bubbles, but do they actually contribute to the harm in decompression sickness? Well, we've certainly seen evidence for that in animal studies. So this is a study, relatively recent study by Kate Lambrecht's group, which showed that a potent antiplatelet agent had a protective effect from decompression sickness in rats. And there are several other studies like this, which haven't actually, it's interesting, they haven't translated into human, certainly not widely into human work yet, but this is a great example of one of the opportunities for low-hanging fruit type research that would exist in our field. A study of antiplatelet agents in treatment of decompression sickness would be quite interesting. Moving on from platelets, I want to talk briefly about leukocyte activation. So this was a paper by Des Gorman in the late 80s, published in Stroke in 1990, where he exposed rabbits to different doses of intracarotid air and watched what happened to cerebral blood flow over time afterwards. So what you see in the graph is time on the x-axis and cerebral blood flow relative to baseline, 100% baseline on the y-axis. And the open circles are control animals, which essentially didn't change. And then 2 different doses of intracarotid air caused this progressive decline. Not a sort of stepwise decline. It actually occurred over time. In fact, most of these bubbles were seen to redistribute rather than obstruct vessels. They were doing this experiment under a dissecting microscope. And they saw these bubbles redistribute, so flow was restored, but then over time, the flow progressively declined, as you can see. And it didn't really matter what the dose of air was, you saw this progressive decline in flow. The fascinating thing about this was that when they rendered these animals leukopenic prior to the experiment, that effect was obliterated. You didn't see it. So this was evidence that bubble passage through blood vessels was damaging the blood vessels, and that subsequently leukocytes were coming along and adhering to the vessel walls and causing a secondary inflammatory change and obstruction. Now, there's more evidence for this, and these aren't the only 2 studies, but this is a more recent study by Weigang Zhu's group in China, published in 2016. Basically, rats subjected to a deep, long pressure exposure that were decompressed either slowly or rapidly. The slow decompression animals formed a small number of venous gas emboli, whereas the fast decompression animals formed a lot of venous gas emboli, a lot of bubbles. And what these micrographs show is leukocyte infiltration in the slow decompression animals, but much more leukocyte infiltration in the fast decompression animals. So this is lung tissue. These are sections of lung tissue. And if you compare both of the decompression sections to the control animals, there was a lot more of this sort of perivascular inflammation and leukocyte infiltration into the interstitium of the lung. In the animals that were exposed to bubbles. So again, this is evidence of bubbles inciting an inflammatory response by leukocytes. So just to summarize some of those things I just said, bubbles can activate platelets, they can incite coagulation. We sometimes see disseminated intravascular coagulation in human decompression sickness, although thankfully that's quite rare. They can form microthrombi, decrease perfusion, and they can activate neutrophils. Neutrophils can get activated by damaged endothelium. They will cause reductions in perfusion. They elaborate cytokines. They can cause vasculitic change and adjacent tissue injury. And there are other activations that I haven't spoken about here, just through time constraints. But there's certainly been some evidence over the years that the complement system and other inflammatory protein systems in the blood can be activated. So I think there's a very strong case to be made that bubbles can incite inflammatory change, and that inflammatory change can contribute to the clinical manifestations of decompression sickness. One of the questions, though, that arises is, are there other activators of inflammation in diving that are perhaps independent of bubbles? And that's where we launch into the microparticle story. So this is a line of research that's emerged more or less over the last decade, maybe 12 years, 13 years, and has created a lot of interest. A lot of the research comes out of one lab in the United States, run by a very respected colleague of ours, Steve Thom, and he has pursued this to a substantial degree of detail, and some of his work I'm going to talk about here. So what are microparticles? Many of you will be aware of this, because they're not a diving phenomenon. Microparticle science pervades other areas of medicine, in fact, many others. But these are very small particulate derivatives of cell membranes found in body fluids, but they're present constantly in blood. So everybody on this webinar has microparticles circulating as we speak. The number of them and their nature changes after activations of the relevant cells. And those relevant cells can be platelets, white cells, endothelium, erythrocytes. And they're elevated in disease states. So, sepsis is a classic example, malignancies, you'll see elevations of microparticles. And these little particles, because they take chunks of the parent cell membranes, they will also carry with them cell surface marker proteins that might be pro-inflammatory, or some of them even appear to have a content of pro-inflammatory cytokines and perhaps the mechanisms for producing those cytokines. So they appear to be inflammatory reaction modulators and have an important role in that area. So how is this all kind of weaved into decompression? Well, it was first observed, 10, 12 years ago that decompression appeared to increase microparticles in humans. And of course, that immediately begged the question, well, where are they coming from? And is it bubble formation that caused microparticle production? And in fact, in studies that have tried to address that question, we have inconsistent findings. So some studies suggest that they do, some suggest they don't. Bubbles aren't involved, and others have had mixed results. So that's a hanging question. It is clear, however, from carefully controlled in vitro studies that bubbles can incite relevant cells like endothelium to produce microparticles. So this was one of Wei Gangzhu's studies that showed that cultured rat vascular endothelial cells will produce microparticles when they're incubated with bubbles. So certainly bubbles can incite microparticle production. The key thing about these microparticles was, and this was one of the things that Steve demonstrated fairly early, is that these decompression-related microparticles are capable of activating neutrophils. They can mediate perivascular inflammation in mice. And this immediately created this question, well, what's the role of this potential role of this in decompression sickness? So that kind of shows us that bubbles can incite inflammation in ways that we weren't entirely aware of before it was discovered that bubbles might have a role in generating microparticles. So microparticles are another way in which bubbles can be linked to inflammation. So carrying on with the microparticle story, one of the most intriguing findings to have emerged in recent times is that these microparticles can actually form at depth. In other words, before any bubbles are formed. And so their formation can be completely independent of bubbles. And so that creates this potential for an inflammatory process, some microparticle formation at depth, completely independent of bubble formation, to be contributory to the inflammatory processes that we see in clinical decompression sickness. So fascinating. The story continues. So some of these microparticles that form at depth increase size after decompression, and they can be compressed. In other words, it seems like they contain gas. And Steve's lab subsequently went on to show that they do indeed contain nitrogen dioxide gas. They identified the mechanism of formation for that gas and proposed that these gas-containing microparticles could actually be a form of micronuclei that would allow bubble growth to occur when these tiny microparticles containing gas entered supersaturated tissues. So not only could bubbles be a player in inciting microparticle formation, but microparticles could contribute to bubbling. So now we have identified an inflammatory process that actually might contribute to bubble formation, which of course contributes to clinical decompression sickness. And finally, carrying on with this, just to round off a couple of other studies that have emerged in this microparticle story. One of the questions that obviously arises is, well, look, if we think microparticles are important, are they elevated in divers with decompression sickness? Now, this is ongoing work Steve's doing, but what you might call a preliminary study published in 2015 suggested that, yes, microparticle numbers are increased in all divers, but more so in divers diagnosed with decompression sickness. In other words, sick divers have more microparticles. Now, that doesn't prove causation. It's an association, just like venous bubbles. And indeed, there's an element of the same kind of problems with microparticle numbers in decompression sickness. It's not entirely consistent. So some divers with decompression sickness can have huge numbers of microparticles. Some divers with decompression sickness have less. But overall, if you look at means, in general, divers with decompression sickness have more microparticles. That would hardly be surprising, though, because any kind of injury or disease tend to increase microparticles. And there's one other study I just want to address briefly, because I've heard it misquoted in the literature quite a few times. So in one very intriguing study, Steve and his group dived mice, and then in a dive that incited decompression sickness, but one of the outcome measures they were monitoring in those mice was pituitary action potential broadening. And they took microparticles from those mice and injected them into non-dived mice and found the same action potential broadening in those non-dived mice. Now, that study has often been cited as taking microparticles from mice with decompression sickness and inducing decompression sickness in non-dived mice, which is not actually what happened. What was shown was this transferal of pituitary action potential broadening. So it's not quite the same. And I think that that's an important point, because they didn't take microparticles from dived mice and induce decompression sickness in non-dived mice. They induced pituitary action potential broadening. And, we see this kind of thing. So this is... this came from a training agency website, and it basically says, when endothelial cells are damaged, for example, when bubbles hit the walls of a blood vessel, then fragments of these cells enter the circulation. They're known as microparticles. A fascinating study was presented that appeared to show microparticles from a mouse that had been decompressed could be transfused into a second mouse who then developed decompression sickness, even though the second mouse had not been under pressure. It's not correct to say that. And I just think that's an important point, because, that being able to induce decompression sickness in a non-dived animal by injecting microparticles from a dived animal would be very powerful evidence that microparticles independently cause decompression sickness. But we're not there yet. So, look, how do we put all this together? And I listened to a presentation by Steve a few years ago at the ONR review, the ONR program review, and he put up a diagram which I've, with his permission, have sort of slightly adapted, and I thought it was a really good, rational attempt to bring all this into one kind of picture. And so I'm just going to show you. It looks a bit busy, but I'll just walk you through it. So we'll start over here. So this is an attempt to put microparticles into perspective in the pathophysiology of decompression sickness, but alongside the other players that are obviously important, so bubbles. And so we'll start over here with high pressure plus or minus oxidative stress forming microparticles at depth. So I mentioned this issue of microparticles being able to form at depth a little bit earlier, and we're not actually sure why that happens. But something is provoking that. And one of the possibilities is the fact that divers breathe higher pressures of oxygen, and there's a degree of oxidative stress which could induce microparticle production. And some of these microparticles will be pro-inflammatory, so working our way around this diagram, some of them are pro-inflammatory, some of them contain nitrogen dioxide gas. Then we decompress. And especially these gas-containing microparticles can enlarge and undergo modifications that make them more pro-inflammatory. And those microparticles containing gas, along with other micronuclei, can be converted into bubbles, because supersaturated gas will diffuse into these micronuclei, or these gas-containing microparticles cause bubble formation. Bubbles can then cause shear stress on blood vessel walls and activate more microparticles. And then bubbles, of course, can have all the effects that we've commonly associated with bubbles in decompression sickness. And I alluded to some of those earlier on in the presentation, my 5-point case that bubbles are the primary vector of injury. Of course, bubbles themselves and these activated microparticles can incite neutrophils and platelets to activate, and this will cause vascular leak, bubbles causing ischemia, bubbles causing a tissue injury, microparticles contributing to these processes, leading to the manifestations of decompression sickness. And of course, this progressive vascular inflammation can incite the production of more microparticles. And look, that's an attempt to bring all these processes together and to meld the story of inflammation and bubbling into one sort of plausible summary. Now, it's true to say that there have been some enthusiasts for, the inflammation story who've basically said, well, why can't it just be inflammation? So the steps that are within that green line that I've just put up there, why do bubbles have to be involved at all? And, what bubbles might just be a sort of a diving epiphenomenon, and it's all about microparticles and inflammation. Well, look, I think there are a couple of holes in that argument you could drive a Mack truck through, and I'll present those to you because I think it's important to have perspective on this. This idea that something like high pressure and oxidative stress during a dive can incite inflammation, and that decompression sickness is thereafter all about inflammation. And I've heard this. This argument came up at a rebreather meeting I was at in Italy just a couple of years ago, before COVID, where it was even argued that you might be better off not breathing as much oxygen during a dive because of this oxidative stress, and that maybe you don't even want to decompress for as long as you do, because decompression on oxygen creates oxidative stress and it might incite inflammation. And this just goes against everything we've learned about decompression and its effect on risk of decompression sickness. Everything we've learned for decades, the longer the decompression you do, the less the risk of decompression sickness. But anyway, there are holes in this argument that I will describe to you now. So why is decompression sickness not only about microparticles? Well, argument one is altitude decompression sickness. I mean, right there, you have an example of decompression sickness that can't be due to pressure and oxidative stress causing formation of microparticles. You're at atmospheric pressure, at sea level pressure, breathing air, no oxidative stress, no pressure. You ascend to altitude in a plane that's unpressurized to 40,000, 50,000 feet. You get decompression sickness. It can't be due to those processes that were inside that green line on that previous diagram. The second point is that if microparticles were the sole problem, and I think this is really important, why would a PFO be important? The lung won't filter microparticles. They're less than 1 micron in size, so they'll just go straight through the lung. The fact that PFOs are important suggests that something the lungs filter but can cross a PFO is important in the pathophysiology of decompression sickness. That cannot apply to microparticles. They will not be filtered by the lungs. They're tiny things that will go through the lung circulation. A couple of other points. These microparticles circulate. So if they were the primary vectors of injury, why are sensitive organs or injury-prone organs that receive luxury perfusion, like the brain, the lung, the liver, the kidney, why aren't they preferentially injured? Why is it organs like the spinal cord and the ear? And we have good explanations for those in relation to bubbles, but it's harder to see why a tiny circulating and pro-inflammatory agent would not injure those other organs like the brain, the lung, the liver, the kidney, which we don't really see that much in decompression sickness. We see huge microparticle elevations in other conditions like sepsis, but those patients don't suffer decompression sickness, so that's another issue. I mean, to be fair, the microparticles that arise in diving may be different in some way, and that's true. So that's not it's not a watertight argument, but it's definitely a point. And I come back to that response to early recompression. If the early symptoms of decompression sickness were due to microparticles and an established inflammatory process, it's really unlikely you would see relief of symptoms just by merely recompressing someone, relief of symptoms during the recompression phase of the recompression. It'd be very unlikely that you would see that. And yet we do see it. And that's more likely explained, or more plausibly explained, by compression of bubbles. So there's just some points about why it's not just about the things that are in that green line that I showed you on that diagram before. It's not just about microparticles. So coming back to the original question, the premise for this presentation, is it bubbles or is it inflammation or both? I presented to you my 5-point case for bubbles being a primary vector of injury. However, I've also presented very strong evidence that inflammatory processes initiated by bubbles, and potentially to some extent independent of bubble formation, so the microparticle story, can be involved. And so I actually think the answer is actually both. I think fairly clearly both. So the way I kind of envisage it is something like this, that if you look at the relative importance of bubbles and inflammation over time after surfacing, then bubbles are the most important thing initially. And that reflects the fact that they probably are the thing that incites most of the inflammatory change. But some inflammation may be possible independent of bubble formation. There's no question about that. And that double-ended arrow is there to indicate that bubbling and inflammation interact with each other. It's even possible that some inflammatory processes, like gas-containing microparticle formation, could influence bubble formation. But over time, inflammatory change becomes more important and bubbling becomes less important. And that kind of reflects the fact that over time, it becomes more difficult to treat divers with recompression. We know that with a delay to recompression, the chances of not making a full recovery in serious neurological decompression sickness increase. And that almost certainly reflects the fact that we're now trying to treat a pathophysiological process, inflammation, with a modality that's not so well designed to treat inflammation. It's very well designed to treat bubbles, and that's why it works very early. I'm talking about recompression, but not so much when you exhibit it late. So that's my sort of intellectual concept of the relation between bubbling and inflammation in decompression sickness pathophysiology. And with that, I'll finish, and I'm happy to take questions. I'll stop sharing my screen and this is a photograph from just a month or so ago. I spent 5 weeks down in the subantarctic south of New Zealand looking for a shipwreck, actually, which we didn't find, but having an amazing time in this sort of open air zoo that is a place called the Auckland Islands. Extraordinary, lots of diving with marine mammals and luckily not great white sharks, although I'm sure there were a few looking at us that we didn't see. So I'm going to stop sharing at this point. I'll just exit and hopefully
There we go.
if I minimize this, I should come into view now. Yeah, I can see Mornay and
yeah, there we go. So Simon or Professor Mitchell, thank you very much for the talk. We've got quite a number of questions here, and I just want to see if you can can see them when I display them on the screen via your computer. I don't know if you can see that there.
Yeah, I can see them. Yeah.
So you're happy for me to display them like that, and then we can just take them one by one, or would you like to?
Yeah, whatever you want to do, Morne. I'm
right.
cool with exactly that. So we
Okay,
can work
perfect.
through them. So the talk that the question is referring to relates to deep stops and decompression strategies for technical diving. The algorithm, look, the short answer to that question is the algorithm's not available. Various people have made up their own, but no, it's not a commercially available algorithm. It's probably best seen as a research tool that we've used for demonstrating the difference in tissue supersaturation patterns between decompressions that emphasize deep stops versus decompressions that emphasize deep stops less. So I'm afraid not. It's a great visual demonstration, though, isn't it? I can imagine why you're asking, but it's not available. No.
So, Aaron, I hope that answers your question. He did follow it up with this remark as well.
Yeah. Yeah. No, of course. And look, the world is trending in this way. The thing about those heat maps that were designed by a guy, I should credit the author of those heat maps, Kevin Watts from the United States. The thing about those is that they were designed to illustrate some principles related to very cutting edge stuff. So it always takes years for that kind of thing to find its way into commercial application, and one has to be careful. We're still in areas of controversy about decompression, and I don't think we're at a point yet where a dive computer manufacturer would necessarily build features like that into their algorithms so that people could mess with them without a little bit more data being available. But that data is gradually emerging. The whole deep stops debate is still being informed by emerging data. And I think in the fullness of time, we'll see very sophisticated dive computer algorithms that will allow us to look at our decompressions in ways like that. But right now, we don't have that. I'm sure we're trending in that direction, though.
Yeah, those heat maps seem to be popular amongst the folks nowadays. I know that they're used on a regular basis. Let's see where that goes.
They're a good way of demonstrating a principle that is quite difficult to get your head around, especially for someone like me, who's I'm a bit of a mathematical imbecile, but I can look at something and appreciate it. They're a great visual representation of quite complicated concepts. So, yeah.
All right. Well, Aaron, I hope that works for you. We've got a question here from Russell Opland, all the way from South Africa. I know him in particular. So he's got a question there.
Yeah. Hi, Russell. Yes, great question. And you're not the first person to have asked that one. Non-steroidals were actually advocated as prophylaxis for decompression sickness by one of the big training agencies for a while. I think they've moved away from that now, but I should also point out that, and this is perhaps self-indulgent, but the only randomized double-blind controlled trial of anything in decompression sickness treatment is a randomized trial of non-steroidal anti-inflammatories as an adjunct to recompression in treatment of decompression sickness. We published that paper, it's almost 20 years old now. It was quite a good study. It was a biggish study, a couple of hundred divers randomized to receive a non-steroidal or a placebo in conjunction with recompression. And what we showed was the people who got the non-steroidal had less requirement for recompressions to reach plateau or complete recovery, but there was no difference in the final outcome. And some people criticize the study for just, were you just treating the pain with the non-steroidal? And our response to that was, well, who cares? If they get better quicker and their final outcome is the same, then whether we're treating the pain or some other underlying thing, then who cares? So there is evidence that non-steroidals are beneficial in treating decompression sickness. That's a little bit different to preventing it. The corticosteroid story is interesting. It's obvious, isn't it? It's the obvious question. If there's so much inflammation in decompression sickness, why don't we treat it with steroids? And it's been tried. Well, it's been tried in animals. So there's now multiple animal studies looking at steroids in decompression sickness. And I can tell you somewhat counterintuitively that all of them have shown either no benefit or a disadvantage. Now, that's not the only allegedly inflammatory disease in which corticosteroids have not lived up to their promise in human medicine. There's no question about that. There's no human studies, by the way, of corticosteroids in decompression sickness, multiple animal studies. So when I say we, I mean the Adjunctive Therapies Committee of the UHMS do not recommend corticosteroids because there's no evidence supporting it. I can tell you, though, that if you get decompression sickness in Europe and you're seriously ill and you go to a hyperbaric chamber, you'll probably get given methylpred because they believe in it there. But I think they believe in it based on the intuition that they're steroids, they must help, but there's no evidence. And in fact, the animal evidence is against a positive benefit. So no, I mean, I don't think there's any basis for using prophylactic anti-inflammatories. There's no evidential basis for it. There's a theoretical basis for it, obviously, from this discussion we've just had. But the caveat is that corticosteroids have not proven to be useful in animal models of decompression sickness. So one wonders whether you should be taking them prophylactically either. Probably not. I mean, I wouldn't. And I, even as an author on that non-steroidal paper, I don't pop ibuprofen before I go technical diving. Yeah. So long-winded answer, but it's a complicated question, like most of these things.
Yeah. And that's a lovely question and even better answer. So, wow. Okay. All right. So we got Philip next. He's got that question.
Yeah. Yes. So does the nature of the gas forming the bubbles affect the nature of the inflammatory reaction? Nothing's simple in this game, right? So I think, so here's my take on this. I think once you've formed a bubble and that bubble is passing through a blood vessel and interacting with the endothelium in the way that bubbles do, I don't think it makes any difference whether the gas is nitrogen or helium or something else. However, there is evidence that certain gases can have anti-inflammatory effects, and there's been quite a lot of interest in helium in that regard. So there is some evidence in the literature that breathing helium can be a neuroprotective agent, and there's actually quite strong evidence for argon in that area, but that's not saying that it's better to have an argon bubble going through a blood vessel than a nitrogen bubble. What the evidence is that breathing argon is anti-inflammatory and can turn off certain injurious processes in disease. So there's two different things there. It's breathing the gas and having the gas in your body in the same sense as having a drug versus a bubble composed of that gas. And I think once the gas is a bubble, it probably doesn't harm you in a different way to bubbles formed from a different gas. But there is some evidence that certain gases are anti-inflammatory, and there's been some interest in helium and argon, but that's a developing field, so that we're talking cutting edge science here, and there's ongoing work with that. We're actually quite interested in argon, not necessarily even in decompression sickness, but in the wider area of medicine, neuroprotection, in all sorts of areas, like cardiac surgery, neurosurgery. Argon is an agent of interest. But I don't think it makes a difference if you've got an argon bubble versus a nitrogen bubble versus a helium bubble causing damage to endothelium. Yeah.
Okay. And then I thought just add this in to say, Smith and Sale says, love these talks. Thank you, Prof. Well, just like to say thanks to the 30-odd folks that are still on the call. Great to have you on here. Next question is from Ragnar. And I don't know if it's very similar to the previous one, but there's hints of it in there at least, I suppose.
No, so, well, some aspects of that were mentioned in the talk. So, formation of microparticles, for example, is an inflammatory process. So, one interpretation of what you've said there, Ragnar, is that, formation of microparticles is an inflammatory process, like an exciting inflammation. And we know from Steve's work that some of these microparticles contain gas, and that those microparticles that contain gas might act as bubble micronuclei and make bubble formation more likely. So from that perspective, the answer to your question would be yes. However, if you were asking me, say, if someone has got an inflammatory problem and they've got inflammatory activations going on, like, rheumatic disease or a concurrent viral illness, if the inflammation that arises from that could make bubble formation more likely on a dive, I think the answer is I'd have to say I don't know, and I don't think anyone does. There's been speculation about it, but I'm not sure that I'm not aware of any evidence that would support a hypothesis like that. But certainly there are certain inflammatory processes, some of which I mentioned in my presentation, like microparticles that form gas, that contain gas, that certainly could make it's a plausible seed for bubble formation. So the answer to your question is sort of yes, but not all inflammation.
All right, thank you. You've got another question from Russell.
Yeah, antioxidants. Yeah, I don't know. I think, again, that's some of these questions, let me say, are illustrative of one of the super cool things about our field, right? That there are so many things that, the discussions that take place in an evidence vacuum. And one of the cool things about diving medicine is there are still all these low-hanging fruit that, questions that in any other field would have been answered, 30 or 40 years ago. But because there's not much funding for diving medicine research, there's still all this stuff. There's still all these really neat questions that are waiting to be answered by enthusiastic researchers. So that's just a little gratuitous advertising for, young scientists to come into our field and answer these practically relevant questions. So this is one that's been asked, okay, so if oxidative stress is part of what kicks off microparticle formation, and those microparticles contain gas and they can act as micronuclei for bubble formation, what would antioxidants be a good idea? And well, lots of people have asked that question, but no one's actually studied it properly yet. So I don't have the answer, but there's a great, well, look, I need to back off and say, to some extent, there has been the Europeans, guys like Peter Jumonpré and Costantino Balestra, they've dabbled in this a little bit. So, for example, they published a study that showed that dark chocolate, which allegedly contains antioxidants, was able to, it changed the post-dive behavior of peripheral blood vessels, which they were attributing to those changes in peripheral blood vessels, they were attributing to bubble formation. And that's about 3 or 4 steps away from suggesting that antioxidants are good for decompression sickness or preventing decompression sickness. And that line of research has never really been followed up on. I must say I was really distressed to go on a dive boat in the Mediterranean and find everyone chowing dark chocolate before they jumped in the water, based on that study, because it's still a lot, there's multiple steps of research steps that need to take place before you could say that the antioxidant effect of dark chocolate is good for preventing decompression sickness. But it's a great perceptive question. Clearly there are people interested in this, and some research has been done, but it's not definitive by any means. So antioxidant research is a great area for. There's a lot of interest in this for preventing decompression sickness, for preventing cerebral oxygen toxicity. Antioxidants are a hot topic area, but I don't think we have any definitive data yet.
So, Professor Mitchell, for any of those folks who want to make money off possibly branding dark chocolate and selling it to divers, they must maybe just hold off on that for a bit. So before I go on, I just want to warn you, there are quite a lot of questions, and I don't know how much time you have still available. Are you keen still to keep going? Or
I'm okay. I don't, I can imagine that everyone on the call is losing the will to live, but and by the way, call me Simon Mornay. This formality doesn't sit well with me. No, fill your boots, go for it. I'm happy to carry on as long as there's people interested.
All right. So some of the questions, just like this particular one from GB, seems very similar to one that we received earlier, but I don't want to make assumptions, and I'll rather allow you to just have a look at it before I just let them be. There is a follow-up question to this particular first question from GB, but I don't know.
Well, this is the same kind of the same question as one that got asked before. The answer is we don't really know. The only data we have on non-steroidals is in treatment of decompression sickness, and the steroids. I pointed out the steroids. Again, there are data in animal studies of treating decompression sickness with corticosteroids, which have not been encouraging. In fact, almost discouraging. I can't explain why. It seems intuitively obvious that steroids should be beneficial, but they do not appear to be. So the answer there, based on the current state of our evidence, is no. Other than to say that if you get decompression sickness and are treated in a hyperbaric chamber, in a lot of places they might add a non-steroidal anti-inflammatory as an adjunct to recompression, and that has human randomized controlled trial data to support it. But that's the only agent that does, and the others are all speculative.
All right, so here's the follow-up, and that's more to do with the research from what I gather reading this question.
Well, good question. I think, it would be a great question to try plasmapheresis or, other methods of reducing inflammatory mediators in an experimental model of decompression sickness. Great thought. To my knowledge, it's not been done. A lot of these answers, obviously I'm having to do them out of my head without being able to jump on Medline and just check that I haven't missed something. I watch the literature pretty carefully, and I think I know most of it, but I can't exclude the possibility that someone somewhere might have done this, but I don't think so. And plasmapheresis is a way of, it's out of my area of expertise, but it's a way of removing unwanted mediators of various sorts from the circulation. And it's a complicated process, and it's a little bit difficult off the top of my head to see how plasmapheresis would fit into our care map of a sick diver. You have to put in a plasmapheresis line, and they have to go in on a machine, and that would probably interrupt recompression therapy. It's hard. It's a little bit hard to see, but as an intellectual question, it'd be fascinating to do it in an animal model. So yeah, good idea.
So Simon, do you think, just compared to other industries, sports, etc., throughout the world, taking diving being quite, I guess, niche, if you want to call it that, and you have this issue called decompression sickness, and you have folks that might have an interest in it, like yourself, to study it further, and I don't know, people that produce drugs, etc., to assist people in general. The appetite, I guess, to sort of really delve deep into some of these things, with the exception of the few like yourself in the world, most probably is why, and also coupled to how often people get bent compared to the risks involved, etc. Does that sort of put the folks that maybe would produce certain things, make them less interested in doing that, or is that not necessarily the case?
Your question basically pertains to the issue of research funding for things like diving medicine, and that's the problem. It's not an issue of global priority for research funding. I can tell you, and some of my colleagues on this call will laugh at this, but if you will sort of laugh, if you go to a traditional medical research funding organization and say, look, I want money to study the consequences of a discretionary recreational activity that's indulged in mainly by middle class males, they're just going to laugh at you, and these days, unless it's kind of child cancer or COVID, it's very hard to get research money. We're deeply grateful for the money we get from organizations like the US Navy Office of Naval Research and my specialty college, the College of Anaesthetists, who support research in diving medicine. But man, it's hard. It's so hard. And that's why there are these low-hanging fruit questions, because it's so hard to get money. And I don't know what the answer to that is. One would think that you might get support from industry, but most diving industry groups will tell you that that they're struggling and that they don't have a lot of discretionary money for spending on things like research. So it's tough. There are some who do this. Shearwater Research, the computer manufacturers, they are supportive of research and have supported our research, and other people around the world. There are some really good examples of companies trying to do the right thing, but man, no, it's really hard, and that's part of the problem. Research funding is a major issue. Yeah.
I'll ask the question just to sort of highlight that, it's always nice to read the papers and the articles and the webinars, but there's a reality that I'm not sure if everybody's aware of. So anyways, let's move on to the next question, which seems very similar to some of the earlier ones. If you felt that you've answered that, we can just...
Yeah, well, I kind of have. We just don't know. This is an area that people have looked at, and there are, interestingly, the focus on taking antioxidative supplements in diving medicine is more on prevention of cerebral oxygen toxicity. There's a lot of interest in that. Things like the ketogenic diet and taking supplemental ketones, to reduce the risk of cerebral oxygen toxicity. No one's really looking hard at prevention of decompression sickness using those kind of strategies, although that dark chocolate thing I mentioned before is kind of an example of that. So we don't know. We just don't know. And over time, I think the answer to that question will become more obvious.
All right. We've got an interesting question here from Rich. And he says, great lecture, by the way. There are studies looking at biomarkers of inflammation, and yes, some of them are elevated after diving, but in some respects, it's not that much different
to study microparticle numbers themselves. I mean, that is an index of inflammation. So there are inflammatory markers that are elevated after dives. I mean, CK is another one that's received a bit of interest, and C-reactive protein has been measured. Various things have been looked at. The problem with it is that none of them have been proven to be useful in making most of that kind of research takes place in the context of trying to find a biomarker that will help with diagnosis. You know, a test, like, does a diver have decompression sickness? Let's take a blood test. Is there something we can look at that will tell us the answer to that question? And the answer is, unfortunately, no. There's nothing that's got enough sensitivity and specificity to do that. So those things have been looked at, but and, you know, not surprisingly, we do find that there are markers of inflammation that are elevated, just like microparticles are after diving. But at the moment, we haven't distilled those findings into anything that's particularly useful to us, like as in studying, finding a test that helps us diagnose decompression sickness.
Yeah, correct. So we have a statement just from Michael. I don't know if you know this particular person. He says he's going to send you a paper.
Do know, I suspect. Yeah.
Okay.
Yeah, he actually sent me I saw something pop up from him. Oh, you know, the paper he's talking about, I know about. I mean, it's a paper that it's another hypothesis paper on how bubbles might form.
Okay.
Yeah.
All right. So we got Lucas there. Okay.
I don't know. Well, look, go right back. Lucas, go back to that diagram that I showed at the end, and I'd say that percentage changes. You know, I think that when you surface, it's all, but you know, it's close to 100% bubbles, with possibly a small contribution to that bubble formation by inflammatory processes like gas-containing microparticle formation. Maybe, who knows? But it's, you know, when you surface, it's 100% bubbles, but then those bubbles incite inflammation, and bubbles start to involute, because that's what bubbles do over time. So bubbles become less important, and the inflammation becomes more important. So those relative percentages are changing over the period after your dive. Like I say, bubbles at first, most important. Then as time goes on, inflammation becomes more important. And that helps us explain why recompression becomes less effective as time goes on. Because although recompression and hyperbaric oxygen is anti-inflammatory to some extent, you know, it's not a perfect anti-inflammatory agent. And as inflammation becomes quantitatively more important in the pathophysiological process over time, then it becomes more difficult to treat with recompression. But yeah, I think the answer to your question is that percentage changes from the moment you surface to the over time. It changes. Bubbles at first, and then inflammation later.
All right, so I'm not going to attempt the name there, but I assume it's David. Has a question there again.
If microparticles is responsible for decompression sickness or inflammation, let's just say inflammation, not just microparticles, but you know, there's inflammation and decompression sickness is not all microparticles. I spend a lot of time talking about it because there's so much interest in microparticles through Steve's work, but look, I don't know the answer to that question, and I think I said that. I might have neglected to say it, but you know, it's the obvious thing, isn't it? You know, like, oh well, we've got this disease process where we think inflammation is important. Why don't corticosteroids work? Well, they don't appear to work in animal models, and it's not just one study. There are about 5 or 6 studies that were done during the 80s and 90s that have looked at this in large animal models, including pigs. And steroids didn't work. And in fact, in one of those big pig studies, in fact, several of the studies, they showed that corticosteroids appeared to be disadvantageous. But why that would be, I don't know. I'm not sufficiently expert in corticosteroid pharmacology to speculate on that. So I kind of just be making it up. I just don't know. It seems weird, doesn't it? And in fact, the Europeans or certain groups in Europe are so confident that the theoretical so confident in the theoretical attraction of steroids that they still use them despite that animal evidence. And presumably that's fueled by the fact that they give steroids to people and they get better. But, you know, they could have been going to get better anyway. Well, they might have even got more better if they hadn't given the steroids. Until we have a proper randomized study, that's why we do randomized studies, right? We'll never know the answer to that question. Not really. But certainly the animal studies are discouraging. And I don't know why.
All right. Well, David, I hope that works. Here's one from another Simon.
Yeah. Well, this has been done. You know, it's what the animal studies, that's what they did. But they didn't work. I mean, all these questions that are coming up about steroids reflect exactly what I'm saying. You know, people can't believe that steroids wouldn't work if inflammation is important. I don't know why. I mean, it's not the only inflammatory disease where steroids haven't necessarily fulfilled their promise, or the extent to which they have is debated. Spinal injury is another somewhat controversial area for steroids, where there was big enthusiasm initially and then kind of buttoned off a little bit as more research got done. But anyway, I don't know. But the animal studies did exactly that. They looked at. I probably should have put the slides up so you could look them up. It's not hard. They're not hard to find though. They looked at that corticosteroids right from the bat, but they didn't work. Yeah, unfortunately.
Okay. All right. So here is a question from Harold. I'm going to see. I don't want to exclude them, just in case.
No.
Something else
so the thing is, just to go back and say that what Steve has shown is that there's a subpopulation of microparticles that actually contain small amounts of gas. So they expand slightly on decompression, and they can be reduced in size by compression. So they, by definition, it looks like they contain gas, and he's even identified the gas. And so, yeah, I think what you're saying is exactly what does happen. So these microparticles introduced into the circulation, they'll circulate through the arterial system and enter a tissue that has supersaturated gas in it after a dive. In other words, the gas pressures in the tissue are higher than the ambient pressure. And if you put a tiny bubble in an environment like that, then the gas will tend the supersaturated gas will tend to diffuse into that small bubble, the tiny bubble, the microparticle that contains the gas, and then it will form a larger bubble. So that's exactly what we think can happen. That's true. That's right.
All right. Here's a slightly different question aimed at you from what I presume is Loic. Your top 3 diving-related books.
Oh gosh, it's like asking people what their favorite
dives,
favorite children, or favorite dive site. Yeah. Well, look. Well, first of all, the Bennett and Elliott's Medicine and Physiology of Diving hasn't been published for 20 years, and yet it remains a standard work in the field. In terms of detailed academic reference works, that is the one. You probably can't get it anymore. And thankfully, there's an initiative now being led by Charles Azzopardi out of Malta to generate another Bennett and Elliott. It won't be called Bennett and Elliott, but it'll be an equivalent book that's being supported by Oxford University Press. So that's likely to happen in the next year or so. And that's very exciting. Aquanaut by Rick Stanton, very recent book. Fascinating guy, really understated guy. Is an awesome book, and of course was written in the aftermath of the Thailand cave rescue. I like that book. And another book that came out of that too, and I can't remember the exact name, was the one that was written by Richard Harris and Craig Challen. In terms of diving adventure, like, wow. And I mean, these are all friends of mine who, whose stories I know quite intimately, the Thailand thing, but the books are just really well done. But yeah, there you go. There's a few books that are worth reading.
Okay. Awesome.
Yeah.
All right. So another question here from Mike.
The same dive, decompressing helium is 3 times more accident prone than nitrogen. So we could have a whole we could have a whole lecture on that. That's interpretation of that statement is so context sensitive. So it depends how you decompress and whether you believe helium needs to be treated differently to nitrogen as a decompression gas, and whether you account for that in your decompression. Overall, I don't think the data. Helium gets used for deep dives, right? So deep diving is associated with a much higher incidence of decompression sickness. So right there, you've got an argument that helium is an evil gas, but actually it's probably just an epiphenomenon. We just happen to use helium for deep diving, so it gets associated with this high risk of decompression sickness that comes from deep diving. I don't think. Yeah, helium is a different gas. There's no question about that. But man, this is a complicated topic, and I think so long as you account for the gas that you're using and you decompress appropriately to the depth and time, and remembering that helium is used for deeper diving, I don't think that there's a strong case for helium being more accident prone. There were a couple of studies that were published by Dick Van through UHM, maybe even only as abstracts a few years ago, where there was a suggestion that nitrogen actually produced more decompression sickness in terms of numbers of cases, but that most of those cases were musculoskeletal and relatively mild, whereas helium produced more neurological decompression sickness, which is what we worry about more. But that might have been more related to the kind of diving that was being done than the actual gases themselves. So it's a very complicated question, and I'd be cautious about, and I'm not rubbishing the idea. I'm just saying be cautious in the interpretation, because it's a very difficult question to interpret.
All right. Interesting name. So there's a different type of question, I guess.
Thank you for your kind words. What are we interested in? Well, we've got lots of projects on at the moment. I supervise 3 or 4 PhD students, and they're studying different things like it's not all decompression sickness related. In fact, most of our work at the current time isn't. I'm working on quantitative EEG methods for measuring narcosis and other gas toxicities underwater. We've got some really interesting work coming up looking at whether pre-exposure to hypoxia or hypercapnia can make divers more likely to recognize it during a real-world dive later on. And we're doing some interesting randomized crossover studies to look at that question. So these are developing training strategies for divers. We have a study at the moment I have one student looking at the effect of bubbles going through the cerebral circulation on cerebral autoregulation. And that study is actually being done in humans. And we can do it because we're utilizing the fact that cardiac surgery patients get exposed to cerebral bubbles during their operations quite a lot. And so we're able to study them legitimately without having, we're obviously not intentionally exposing them to bubbles. It just happens as a result of their surgery. So that's really exciting stuff, and it's human. So those are some examples of things. I'm involved in a little bit of work with David Dulett at the moment, looking at the pathophysiology of inner ear decompression sickness and saturation diving, and whether it's the same or different to pathophysiology of inner ear decompression sickness and sort of bounce diving that we typically do in technical dives. That's kind of very sort of niche, a very niche area. There's some examples. And we are lucky in that we do have funding from the US Navy, and we're deeply grateful for that. If anyone from the US Navy is watching this, there are very, very few organizations. The US Navy is one, and Dan is another. Dan has these businesses that create an income stream, which they then plow back into research, which is awesome stuff. But not, it's not huge amounts of money, but it's money. And, Dan is one of the other organizations that really does have a capability of funding research. So maybe more Dan America than I don't know about Dan Southern Africa. Mornay, I'm not trying to commit you to forking out money for research. It's tough.
Yeah. Yes, I think, just based on our size versus, say, the folks from the States and so forth. But obviously we have contributors in the form of Jack and so forth, and CJ, as you mentioned, and those type of things. All right, well, interesting studies, and I can see just further down, a lot of people are commenting on the enthusiasm to, I guess, see the results of those in time to come. So, watch the space, I suppose. There's another question from Peter. That is a question.
Oh, well, I think by definition, most autoimmune conditions are considered. I mean, this isn't my area of expertise. You'd want to ask a rheumatologist or, one of those people in that area. But, I think autoimmune diseases are considered inflammatory diseases. I think the two mesh quite tightly. So yes, I think there's lots of linkages there. I think autoimmune processes are by definition inflammatory. It's inflammation that results in the damage to tissues. Autoimmune responses create inflammation, and inflammation causes the clinical manifestation. So yes, they are, but certainly not my area of expertise.
All right. We got another question from Loic here.
ODIVE. Yeah. Look, we're interested in this idea of self-monitoring, and look at it. In the fullness of time, this may well become something that everybody does. But I think what I would say at this point in time is that we don't have the data to support the notion that these devices could reduce the incidence of decompression sickness. So that work needs to be done. There's another example of a great opportunity for research. Like ODIVE controlled diving versus non-ODIVE controlled diving would be a really interesting study. We've actually purchased an ODIVE, the technical diving device, and we fully intend to look at it. There's been one or two papers published looking at the utility of the ODIVE, but not its ability to reduce decompression sickness, but just how easy it is to use and the information that it gives you, those kind of things. We are interested in looking at it ourselves. The problem is we did that just at the start of the COVID pandemic, and we've had difficulty getting going with our field work, especially large scale field work over the last couple of years. So that's something that's on our books, and we will look at And it may well prove to be, that's its goal. The manufacturer's stated goal is informing dive practice to reduce the risk of decompression sickness by tailoring the dive practice to the individual. And it certainly has merit. But it's an unproven concept at this point in time.
Okay. Then we got Rob now. He's also got a question there for you, Simon.
Yeah, I think this was a question that sort of came up earlier. If you're in an inflammatory state before diving, can that be a cause for bubble formation and therefore decompression sickness? No. The simple answer is no. There's been no study looking at that. There's certainly a lot of speculation on it. For example, there's lots of anecdote about people going diving who've had a recent musculoskeletal injury who, end up with enhanced pain in their injury site after a dive and speculate that it could be caused by bubble formation. But it could just be increased use of that injured, limb or joint or whatever that's provoking the pain rather than bubble formation because of the inflammatory state. Who knows? We don't know. I think in general, there are pretty good arguments for not diving when you're unwell or injured that are separate to the risk of decompression sickness. And as a general rule, I would advise against it. But the specific answer to that question is I don't think we know. It's a good question, though. And it's one that's been speculated on quite a lot.
Okay. So it's a slightly different question to most so far. I think it's quite interesting. I don't know what your take is on that.
Yeah. Well, the main concern with asthmatics is air trapping in the lungs and pulmonary barotrauma, although the real risk of that appears to be, lots of asthmatics do dive. I mean, I clearly wouldn't recommend diving in the middle of an asthma attack, but, people with well-controlled asthma do appear to be able to dive, in asymptomatic periods reasonably safely. But in terms of decompression sickness, as opposed to pulmonary barotrauma and arterial gas embolism, that's an interesting question. There's been speculation that the use of bronchodilators in the pre-dive period to facilitate diving by asthmatics might be a bad idea because it could reduce the efficiency of the lung capillary bed and filtering venous bubbles by bronchodilating the lungs. And there's actually some animal evidence to support that. I think the study was done with aminophylline in animals. It's a little bit hard, to be sure that will translate to humans. But I actually think that that's a very doable study, and we've thought about it a few times, and that is looking at the effect of bronchodilator medication on arterialization of bubbles across pulmonary shunts. That could be done relatively easily and ethically, I believe, by just doing dives with, a bubble-provoking dive and doing cardiac echo or transcranial Doppler or one of those things, and having some subjects breathe nothing, breathe air after the dive and some breathing air after using a bronchodilator. That would be a really interesting study, and I don't believe it's been done in humans. And that's the concern with asthmatics. It's not asthma itself per se, but more likely the medication that might make you more vulnerable to decompression sickness. Obviously, the big concern with asthmatics is pulmonary barotrauma. I talked about that before.
Okay. So interesting. I've seen a couple of guys, and I won't list them all, so please forgive me. But here's one particular chap, Timothy, and I guess it's a spin-off from the research funding discussion we had. And I don't know what your take is on crowdfunding and things like that, but there's been a bit of a discussion there that if it'll benefit divers, they would be willing to contribute. So I don't know if you have any.
Yeah, I'm not aware of anyone who's doing it. And in theory, it's a great idea, but these things are always tricky, aren't they? Because, if you set up a crowdfunding page, then who administers the funding? How do you decide who it goes to? All those things are quite nuanced and hard. But various organizations have done things like this, at small scale, like conference organizers, like the Eurotech people, they were putting the profits of raffles at their dinners and things like that to research, and every little bit helps. But it's a great idea, but it's never as simple as one thinks. But if someone did it, I certainly wouldn't consider it a bad idea. I think it would be amazing, but it would be a significant undertaking to raise a lot of money and then administer it successfully. Yeah.
Well, maybe that's a task for Dan Southern Africa in a way to contribute, and then possibly get, I don't know, a little bunch of folks together and see where we go. I don't know. I'm just spitting out some ideas.
Sort of organization that could do it. You're right. I mean, Dan could do that. That's and Dan. The reason Dan would be suitable is because you have a legitimacy that people would feel confident in. That their money's not just going to disappear into someone's bank account somewhere. And also, one would probably be able to trust Dan to allocate that money to projects sensibly and fairly. So Dan's exactly the sort of group that could do something like that.
So just on the slide, the Dan America folks on their website, they actually have a dedicated space for donations in different sort of formats, be that for research, etc., etc. And as far as I know, Dan Europe now also has that available for any of your folks. Maybe just hop onto their sites and see what's available then and take it further. In between, some folks obviously had to bounce off the webinar, but a lot of praise, thank yous, great talk, and so forth, which I won't add now, but we're getting to the end of the questions. So if you're still fine to go, that's fine. Otherwise, we can leave them for another stage. Simon.
I know. Look, so the David Shaw accident. Anytime you're talking to South African divers, it always seems to come up, even though it's got nothing to do with the topic we were talking about, and that's fine. Look, as you know, I was involved with Franz and Jack and the others. I forget
only Brits.
In investigating that accident. And actually, that accident, poor old Dave. But man, what a legacy! We were able to identify a really important aspect of respiratory physiology that affects deep technical divers and warn other technical divers about it. And I've personally been contacted many times over the years by divers who claim to have got themselves into similar situations, but were able to recognize what was going on because of what happened to Dave and the way it was reported, and have managed to get themselves out of it. So the things that perhaps would have avoided what happened would have been zero work. That's one, but a lighter gas. So Dave's gas was a bit dense for that depth. So less nitrogen, more helium would have helped. And there were also aspects of the equipment setup, so the rebreather itself, that would have increased the work of breathing. That if Dave could have avoided those, then it might have helped. So there's multiple things. But in general, the message I would give deep technical divers is that gas density, planning around gas density, should be just as much a part of the plan as maximum operating depth from a PO2 perspective, and your decompression plan. Gas density should be part of your planning, and aiming to have a gas density lower than, it's hard when you're going really deep, but 6 grams per litre, there's an inflection in the risk of CO2 retention. We've published data on that a few years ago through Gavin Anthony's data from Kinetic. I think, you know, that's the best advice, is to make sure that gas density is part of your planning.
Okay. Here's a question again from Simon, just asking about the book titles and for me to add them in the follow-up email. So I didn't make a note of all the books you mentioned, Simon.
I'll email them to you. I'll
Okay.
email them to you. Yeah.
All right, fantastic. Then I'll add that in. If it's not tomorrow, Simon, it'll be the day after or so. So yeah, just keep a lookout for the emails. Yeah, I think maybe we can take a handful more, and then if there are any other questions left, I could always pass them on, and we can deal with them in time to come. Here's another question from Russell about a publication. I didn't read the question yet.
It sounds like Russell sounds like a physicist. I think off the top of my head, the differences that that arise from applying STPD rather than BTPS, or the various different ways of expressing temperature and pressure effects on gases, I don't think they make a huge amount of difference to the recommendations, to be honest. So I think I'm not aware of any initiative to produce tables that relate to those gases, those data presented in different ways. I think you can use just like this is bucket chemistry rather than, you know, true precise science. And if you just use gas density calculations based on the known densities of the various gases involved, like nitrogen, oxygen, and helium, at atmospheric pressure, without adjusting for the particular, you know, physical temperature issues, I think you'll still get to the right place. I don't think you need to do that. This is an interesting question, and this person, if Russell wanted to contact me offline and demonstrate to me that it would actually make quite a big difference, I'd be interested in hearing that, because Gavin Anthony's an engineer who's very interested in that kind of stuff, and his sense of it was that it wouldn't, and that, you know, divers didn't need to get into that kind of level of detail to successfully plan gas densities. But I'd be interested to hear from Russell if he thinks otherwise.
Okay.
Yeah.
All right. Well, I'll make that connection. So Russell, keep a lookout for mail from our side. All right. Well, we're nearing the end now. We've got a question here from Bo regarding COVID and PCS and so forth.
Yeah. Well, this is a question that comes up. Obviously very topical, and at this point in time kind of difficult to answer, because we're still in the early stages of figuring out how COVID affects diving. Look, the one way in which there has been speculation on this is, again, coming back to that comment I made about asthma and bronchodilators and the pulmonary bubble filter. There's been some concern expressed that that lung damage induced by COVID could reduce the efficiency of the lung's ability to remove venous bubbles from circulation. And if more venous bubbles are able to cross the lung filter into the arterial circulation, then in theory that would increase the risk of decompression sickness. And rather than it being an unpredictable inflammatory response, that's the mechanism, COVID-related mechanism, that most people are focusing on at the moment. In terms of inflammation, I'm not really sure. It comes back to that question about going diving while you're in an inflammatory state. At the moment, most of the sort of consensus guidelines on how to deal with diving after COVID suggest that you need a reasonably substantial period of time to just let everything settle. And that's mainly normalization of any lung changes that might have occurred, which can occur even in relatively asymptomatic people with COVID. So by the time you wait that kind of period, and for many groups it's somewhere around 3 months, before going diving again. Most of the sort of acute inflammation associated with the disease will have settled and gone away. So the main concern with COVID at the moment, we think, is with regard to decompression sickness, is the reduced efficiency of the pulmonary bubble filter. The bigger concern with COVID is that lung changes might predispose to pulmonary barotrauma and, you know, gas trapping in pulmonary barotrauma and arterial gas embolism as a result of that. So that's the main concern with COVID rather than decompression sickness.
Awesome. Okay, but I hope you got that. Sebastian's got a question I was reading, but it didn't make sense to me. But then again, no.
Yeah. Oh no. Well, Sebastian's question reflects a question that came up earlier about autoimmune disease. You know, these are inflammatory diseases, and therefore, you know, like if we're worried about inflammation and decompression sickness, are they more at risk and should they be extra careful? I think we don't know the answer to that question, and as far as being extra careful is concerned, well, you can hardly go wrong by saying that, can you? I mean, I think, you know, most people with severe autoimmune disease probably don't dive. So I think, you know, I think we're probably dealing with subtle degrees of illness here, and probably it doesn't materially increase the risk of decompression sickness, but we don't know that for sure. And so I don't really have, you know, that question, the answer to that question is kind of somewhere in a evidence vacuum. I don't know. I don't know whether they're more at risk or that they should be extra careful, but I suspect, my gut feeling is that most people with autoimmune disease who are able to dive probably don't have a substantial increase in risk.
Okay. All right, well, 2 more questions, and yeah, then we'll call it a day.
No, although a lot of people think that helium is the answer to that question, but of course it's not. You know, there's no, unfortunately, well, oxygen, but you can't breathe oxygen at extreme depth, unfortunately. So no, there's not. There's no gas that, I mean, we have to have a diluent gas for oxygen, and all of those gases, whether it's helium or argon or hydrogen or nitrogen, they all get absorbed, and they can all cause tissue supersaturation during decompression, and they can all cause bubble formation. So no is the answer to that question. We haven't found a gas that you can replace nitrogen without any risks of decompression.
Yeah, well, very last question from the same person, and then yeah, we'll call it a day.
Yeah, okay. The answer to that question depends entirely on the severity of the decompression sickness. So in terms of if you suffer what we refer to as mild decompression sickness, so in that spectrum there would be musculoskeletal pain, a rash, patchy tingling in the skin, which is sometimes seen, that's non-spinal in its origin, or divers with constitutional symptoms like fatigue, they virtually all get better. And in fact, they usually get better no matter what you do, whether you recompress them or not. So the answer to your question in respect of mild disease is that it's near 100% get better. With serious neurological decompression sickness, that changes. So spinal disease with significant spinal symptoms, then the incidence of not making a full recovery at the end of all recompression treatment is something around 40 to 60%. If you go to a chamber with spinal decompression sickness like paralysis, bladder atonia, sensory change in the distal limbs, then yeah, you know, there's a significant chance that you won't make a full recovery. So it's all dependent on severity of disease, and to some extent on the delay to recompression. So very early recompression will almost certainly, even the people with spinal symptoms, they mostly get better if you're very delayed in recompression. So there's lots of nuances to that question. But mild disease, almost all get better. Severe disease, there's a significant proportion who don't. And the medical thing, I think having medical examinations is less about decompression sickness and more about the other things that can cause problems in diving. So, for example, about 25 to 30% of diving fatalities have a cardiac event as the disabling injury. And there are multiple studies that show that. So, obviously as we get older and less fit, then your risk of cardiac disease starts to increase. And so people who are, older divers should very much think about health surveillance as they get older and being monitored for things like blood pressure and having ECGs periodically to look for cardiac changes. And certainly if they start getting cardiac symptoms, getting checked up and making sure that they're properly investigated for those kind of things. So the importance of diving medicals is more for the non-decompression sickness type things that can cause you major problems in the water rather than preventing decompression sickness. But diving medicals are important as we get older. There's no question about that. Or if you're going to go into, even as a young person, if you're going to go into diving with a pre-existing medical condition, you should go and see a diving doctor and find out what the implications of that condition are for diving and what it represents in terms of risk. There's no question about that. I see diving medicals as very important for people with medical issues, perhaps not so important for people who are perfectly fit and well. Like most training organizations these days, they just get you to do a screening questionnaire, and if there's no positive responses, then you can go straight into diving, and that's reasonable. But if you do have pre-existing conditions, you should see a diving doctor.
All right. Well, from my side, thank you very much. We still got about half the folks that joined originally, which, wow, that's amazing. Thank you so much. Obviously, you kept them captivated with all, one, the talk, and then two, with all the questions you answered. So thank you for your time. For all the folks that joined, really appreciate your time. Sure, there's so many thanks and great talk, and thank you for the feedback and so forth. So, thank you guys. Before we go, for the folks that possibly didn't get that QR code scanned, I'll just pop it on the screen again. You can just scan that if you'd like a copy of the Dan Decompression Sickness Guide, and I'll just WhatsApp you the download link. So you're welcome to scan that. It'll just open up a pre-populated WhatsApp message, and I'll then get back to you. So you're more than welcome to use that. Simon, again, thank you so much. It was amazing having you on this talk. I look forward to the other two that we got planned for this year. And I hope you're going to have a great day. It's been a nice early one for you. And sorry about the hiccup right at the start. Until next time, thank you so much.
Yeah, no, all good, Morne. Looking forward to it. So, next time we're going to talk about that blood gas experiment on the free diver. It's kind of an adventure talk as well as a science talk, because we had a lot of fun doing that. So, I look forward to chatting about it.
Awesome. As usual, I'll keep you guys posted on the talk dates and so forth. So that's still in a couple of months' time. Can't remember, around about June, July, if I recall. So that's it from our side. Thank you very much, Simon. Enjoy the rest of your day. And to the folks that are still here, have a nice time. Ciao, ciao. Bye-bye.